Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Imagine trying to write down the distance from the sun to Neptune, but instead of using miles, you have to write it in inches.
Oh, wow. Yeah, that sounds terrible.
Right, and you can't use any scientific shorthand at all. You just have to write a normal standard number.
Your hand would completely cramp up.
Exactly. Your hand would cramp from writing zeros before you even finish the calculation. And honestly, you'd probably lose count of how many zeros you'd written anyway.
Oh, you would absolutely lose count. I mean, when you look at the raw scale of the universe or, even just our own solar system, standard arithmetic breaks down very quickly.
Yeah, it really does.
It becomes this massive, sprawling problem. The numbers get so astronomically huge that simply writing them on a chalkboard becomes a literal physical barrier to doing actual science.
Which brings us perfectly to our focus today. We are doing a deep dive into section 3.8 of chapter 3 from Contemporary Mathematics.
Great section.
It is, and the textbook actually features this incredible NASA image of our solar system, figure 3.44. It shows the sun blazing on one side and the planets just stretching out into the dark.
Yeah, it really puts it into perspective.
It uses that image to illustrate why mathematicians absolutely refuse to write things out the long way. So, for this deep dive, I'm officially stepping into the shoes of the student today, and I am formally acknowledging you as my lecturer to guide both me and you listening at home through this material.
I love it. I will gladly take on the lecture role today.
Awesome. So our mission is to demystify exponents.
That is the mission. We want to transform exponents from this intimidating math jargon into what they really are, which is a highly logical, incredibly necessary, time-saving shorthand.
Because without them, as section 3.8 points out, calculations wouldn't just be difficult, they would literally become an unreadable mess.
Unreadable, yes.
And mess seems like an understatement, honestly. If you're listening and trying to picture what doing math without exponents looks like, just think about texting.
Oh, the texting analogy is perfect.
Right. Like if I'm texting someone that I will be right back, I don't tap out every single letter. I type BRB or LOL instead of laughing out loud.
Yeah, and the textbook actually uses that exact same analogy. You write TLDR for too long, didn't read, to save time and thumb energy.
Exactly. It's just faster.
But that shorthand is incredibly efficient only on one massive condition. The person reading the text has to know the agreed-upon code.
Right. They have to know what those random letters actually mean.
Exactly. They have to know what those letters represent. And exponents are basically just the mathematical version of TL Dr. Vel. They are the shorthand for repeated multiplication.
So instead of writing out a long, exhausting string of the same number multiplying itself over and over, we compress it.
We compress it.
The textbook gives a hilariously tedious example to prove this point. Try writing the number 8 multiplied by itself 19 times.
Just brutal.
Just writing 8 times 8 by the 7th or 8th one, your brain just turns it into visual static.
It really does. There has to be a more efficient way to represent 19 eights lined up in a row. And that's where the terminology of our shorthand comes in.
Okay, let's unpack this terminology.
So to write this efficiently, you write a regular-sized 8, and then you place a tiny 19 raised up in the upper right corner.
Let's lock down the official terms here so we don't get lost later on in the deep dive. If I see a 7 with a little 5 floating next to it, what are we calling those two distinct numbers?
Great question, student. The main number resting on the line, so the 7, is the base.
Base. Gosh.
Think of it as the foundation. That is the specific number being repeatedly multiplied.
Okay, and the little number?
The tiny number floating up top, the 5, is the exponent. And the exponent's only job is to tell you how many times to multiply that base by itself.
So a 7 with a little 5 simply represents 7 multiplied by itself 5 times, 7 to the 5th power. Exactly. So base is the what? Exponent is the how many times. The foundation and the instruction.
You nailed it.
Well, now that I've got the basic shorthand down as your student, the natural hurdle is figuring out how to actually do math with these compressed numbers.
Right, because if you just expand them all out again, you defeat the purpose.
Exactly. If I have to unpack them and write out all those 8s every single time I want to multiply or divide, the shortcut is totally useless.
That exact frustration is why the textbook introduces a set of rules for combining these terms.
Okay, hit me. What's the first rule?
The first tool in the toolkit is the product rule for exponents. Basically, the rule states that if you have a base raised to a power and you multiply it by the exact same base raised to another power, you can simply add the exponents together.
Wait, really? Let's run a real number through that to see how it works on the ground.
Sure, we can use the textbook's example. It gives us 9 to the third power multiplied by 9 to the fifth power.
Okay, 9 to the third times 9 to the fifth.
Let's ignore the shortcut for a second and look at the underlying mechanics.
Yeah.
What does that equation actually look like if you unpack it?
Well, 9 to the third is a cluster of 3 nines multiplying each other, and 9 to the fifth is a cluster of 5 nines multiplying each other.
Right, and if you multiply that first cluster by the second cluster, how many nines do you have lined up in one continuous chain?
Let's see. You have the initial 3 nines plus the 5 nines. So you have 8 nines all multiplying each other in a row.
Which means the final answer is simply 9 to the 8th power.
Wow, okay. That is much faster.
Notice how you avoided calculating the massive actual value of 9 to the third, and you didn't need to find out what 9 to the fifth is.
Right. I definitely didn't want to multiply those two gigantic results together.
You just added the instructions together. 3 nines plus 5 nines means you have 8 nines. 3 plus 5 equals 8.
That feels almost too easy. It feels suspicious.
Yeah.
As a student trying to break the system here, I want to test the limits of this product rule.
Bring it on.
What if the equation is messier? Like, can I use this adding trick to simplify 5 to the 9th power multiplied by 8 to the 4th power?
Okay, I have to throw up a massive stop sign right there.
I know it.
The textbook actually places a giant caution checkpoint in the chapter for this exact scenario. The product rule only functions when the bases are completely identical.
Ah, okay. So no mixing and matching.
Exactly. Think about the physical reality of what you just suggested. If you have 9 5s lined up in a row and you multiply them by 4 8s, you don't magically have 13 of the same number.
Right, because they're different numbers entirely.
You have a mixed bag of 5s and 8s. You can't use a single base to represent a mixed bag. The foundation has to match perfectly for the rule to apply.
The foundation must match. Understood. Let's keep moving through the operations then. If multiplying identical bases means we add the exponents, I'm going to take a leap of logic here about division.
Go for it.
If division is the opposite of multiplication, does the quotient rule mean we divide the exponents?
You know, you would think so. Sounds like a logical mirroring. But let's look at the actual mechanics of division. Let's visualize the textbook's example for the quotient rule. It's 14 to the 13th power divided by 14 to the 6th power. Picture writing that out as a massive fraction on a whiteboard.
Okay, I'm picturing a literal wall of numbers right now. On the top line, the numerator, I have to write out the number 14 multiplied by itself 13 times.
Correct.
And on the bottom line, the denominator, I write out a chain of 6 14s.
Perfect. Now, what happens when you divide a number by itself?
Well, it becomes 1.
Exactly. So start crossing out matches on your whiteboard. For every 14 on the bottom line, cross out a corresponding 14 on the top line.
Oh, I see it. It's actually incredibly satisfying to picture. Cross out one from the bottom, one from the top, slash.
It's going.
Okay, I cross out all 6 of the 14s from the bottom line, which means I have to cross out 6 of the 14s from the top line.
And what are you left with?
The bottom line is completely empty. The top line had 13, I crossed out 6, so I'm left with 7 14s sitting on top.
Which is 14 to the 7th power. The visual crossing out proves the formula.
Oh, yeah.
You didn't divide 13 by 6. You had 13 items, you physically removed 6 of them through cancellation, and you were left with 7. The quotient rule is subtraction.
Subtraction, got it.
When you divide identical bases, you just subtract the bottom exponent from the top exponent.
Subtracting makes total visual sense now. But as I'm picturing this crossing out process, I'm noticing a potential trapdoor here.
Oh, what do you see?
What happens if the top and bottom of that fraction have the exact same exponent?
Okay, let's play this out.
Let's say the problem is 3 to the 6th power divided by 3 to the 6th power. Following your quotient rule, I subtract the bottom exponent from the top. 6 minus 6 is 0.
Yep.
The answer gives me 3 to the power of 0. What in the world is a 0th power? How do you multiply a number by itself 0 times?
What's fascinating here is that you've organically stumbled into the 0 power rule.
Really?
Yes. Following the mechanical steps of the formula led you to a place that sounds like mathematical nonsense, but it actually reveals a huge structural truth about how numbers work.
Okay, I'm intrigued.
Let's look at 3 to the 6th divided by 3 to the 6th again. But forget the exponents entirely for a moment.
Okay, ignoring the little numbers.
Fundamentally, what is the result when you divide any non-zero number by itself? What is 5 divided by 5 or 1,000,000 divided by 1,000,000?
It's always 1.
Right, and 3 to the 6th is just a number. Its actual value is 729, but the value is irrelevant. The equation is basically 729 divided by 729.
A number divided by itself.
Exactly. So 3 to the 6th divided by 3 to the 6th mathematically has to equal 1.
Wait. So if 3 to the 6th divided by 3 to the 6th has to equal 1 because of basic division, but the quotient rule proves that it equals 3 to the power of 0 point. It traps you.
Yes, it does.
3 to the power of 0 literally has to be 1.
The math demands it. Any non-zero base raised to the 0th power equals 1. It is not an arbitrary rule a mathematician invented just to create a headache on a quiz.
It's just logic.
Exactly. It is a necessary, inescapable consequence of division. If the quotient rule is true, the 0 power rule has to be true to prevent math from breaking.
That is wild. It's like discovering the plumbing behind the walls of a house, you know? You suddenly realize why the water flows the way it does. The rules are entirely structural.
They really are. The structure gets a bit more complex, though.
Oh boy.
We've mastered combining identical bases, but textbook equations rarely stay that neat. What happens when we introduce groups of different bases or, start stacking exponents on top of each other?
Let's get into the messy brackets. The textbook introduces the distributive rule for exponents next.
Right. Let's walk through the multiplication version of this rule slowly so we can really visualize the packaging.
Okay, visualizing packages.
Imagine you have a product inside a parenthesis. Let's use 3 times 7. Now, raise that entire parenthesis to the 4th power.
All right, so I'm writing down a parenthesis, 3 times 7, close parenthesis, then another one multiplying next to it, and a third one, and a fourth one. I've got 4 of these identical little packages lined up.
Perfect. Since everything here is just multiplication, and the commutative property tells us we can multiply numbers in any order without changing the result, what happens if you break open all 4 of those packages?
Well, all the 3s and 7s just spill out into one long line. So I guess I can rearrange them. I can slide all 4 of the 3s over into one pile and all 4 of the 7s into another pile.
And how would you write those 2 new, perfectly organized piles using our shorthand?
The pile of 4 3s becomes 3 to the 4th power. The pile of 4 7s becomes 7 to the 4th power. So the whole thing is just 3 to the 4th times 7 to the 4th.
Exactly.
It's the outer exponent basically acted like a delivery driver, dropping off a 4 to every single number inside the parenthesis.
A perfect description. The formula is a times b, in parentheses, to the nth power equals a to the n times b to the n.
That makes total sense.
The textbook also points out this works in reverse, which is highly useful. If you see 7 to the 8th times 11 to the 8th, you can notice they share the same exponent.
Oh, interesting.
Yeah, you can pull that exponent out, multiply the bases together first, so 7 times 11 is 77, and then apply the shared exponent to get 77 to the 8th. But again, the caution checkpoint applies. This only works if the exponents match perfectly.
Right, they have to match. And the distributive property works for fractions too, according to section 3.8.
It sure does.
Like if I have a fraction in a parenthesis, like 3 over 5, and I raise that whole thing to the 7th power, the delivery driver drops a 7 off at the top and the bottom. It just becomes 3 to the 7th over 5 to the 7th. It's a remarkably clean way to dismantle complex fractions.
It cleans things up beautifully.
But I'm looking at the next section, and I'm feeling a mild sense of panic.
Uh-oh. Why is that?
What happens if I take a number that already has an exponent and I raise that entire thing to another exponent?
Stacking them.
Yeah.
Huh.
Let's say my base is 3 to the 6th. I put 3 to the 6th in parentheses and I raise it to the 4th power. Do I add the 6 and the 4? Do I multiply them? Do I raise 6 to the 4th power? It looks crazy.
No panic necessary. Let's just rely on the fundamental logic we've built. This is the power rule. Look at the outermost instruction first. The outer exponent is a 4. What is it telling you to do to the item inside the parenthesis?
It's telling me to multiply the inside item by itself 4 times. So I'm writing out 3 to the 6th times 3 to the 6th times 3 to the 6th times 3 to the 6th.
Now look at what you just wrote.
Yeah.
You have identical bases, all 3s, multiplying each other. This is the very first rule we learned today.
The product rule.
Exactly. When identical bases multiply, what do you do with the exponents?
I add them. 6 plus 6 plus 6 plus 6, that gives me 24.
And what is the mathematical shortcut for adding the number 6 4 times?
Oh, you just multiply 6 times 4.
That is the power rule. When you raise an exponent to another exponent, you simply multiply the 2 exponents together. You don't have to write out the 4 clusters of 6.
You just multiply 6 by 4.
Exactly. And your 3 to the 6th raised to the 4th smoothly becomes 3 to the 24th.
It really is just falling dominoes. Once you understand the basic shorthand, Every single rule is just the natural extension of that first mechanical reality.
You are seeing the architecture of mathematics. We went from basic shorthand to adding exponents to subtracting them with division, discovering the absolute trap of the zero power, distributing exponents into parentheses, and multiplying them when they stack.
That's quite a journey.
It is.
Yeah.
But the textbook leaves one final crucial mystery for us to unpack.
And this is where things go completely upside down. I want to link back to the quotient rule real quick, our division rule, where we visualize crossing out numbers and subtracting the exponents.
Okay, circling back.
Earlier, we divided 14 to the 13th by 14 to the 6th. We subtracted 6 from 13 to get a nice positive 7. But what happens if the bottom number is bigger? What if the denominator's exponent is larger than the numerator's?
Let's set up a scenario.
Let's do 4 to the 5th divided by 4 to the 7th. 5 4s on the top line, 7 4s on the bottom line. If I blindly trust the quotient rule, I have to subtract the bottom from the top. 5 minus 7.
And what does that give you?
That results in a negative number. It gives me 4 to the negative second power. What is a negative exponent? I can't physically multiply a number by itself negative 2 times.
It sounds like science fiction, right?
Yeah.
A negative quantity of a physical action just doesn't make intuitive sense.
Not at all.
But let's trust the logic and expand it manually on our imaginary whiteboard, just like we did with the crossing out method earlier.
Okay, visualizing the fraction. Top line has 5 4s multiplying each other. Bottom line has 7 4s multiplying each other. I start crossing out the pairs.
Walk me through the aftermath of the crossing out.
I cross out all 5 of the 4s from the top line. The top is completely empty, which means a 1 is left as a placeholder.
Correct.
And on the bottom line, I crossed out 5 of the 7 4s, which leaves 2 4s sitting on the bottom line.
So what is your resulting fraction after the dust settles?
It's 1 over 4 squared.
Now let's connect the dots. By blindly following the subtraction formula, you got 4 to the negative 2.
Yeah.
By manually expanding and crossing out the numbers, you got 1 over 4 squared. Those two expressions must be identical. 4 to the negative 2 equals 1 over 4 squared.
Wow.
This is the negative exponent rule. A negative exponent does not turn your base number into a negative number. It creates a fraction.
That is so cool. It's basically a location command. Think of a negative exponent as an elevator ticket. If a number is sitting in the numerator penthouse and it gets a negative exponent, it takes the elevator down to the denominator lobby and becomes positive.
The elevator ticket is a fantastic way to visualize it. And the best part about an elevator is that it goes both ways.
Wait, really?
Yeah, the textbook shows how you can use this rule in reverse to clean up messy division problems. Imagine you have a calculation like 7 to the 3rd divided by 13 to the 9th.
Okay, a fraction with different bases, so I can't combine them.
Right, you can't combine them, but maybe you need to plug this expression into a computer program that hates fractions, or you just want everything written on one flat, clean line. How do you get that 13 to the 9th out of the denominator?
Oh, I see. I use the elevator ticket in reverse. I take that 13 to the 9th from the bottom lobby, move it up to the penthouse line with the 7 to the 3rd, and I slap a negative sign on the exponent to pay for the trip.
Exactly.
It becomes 7 to the 3rd times 13 to the negative 9th.
You've completely flattened the equation. You took a cumbersome fraction and transformed it into a sleek single line of multiplication simply by understanding how negative exponents behave.
If you are listening to this and trying to synthesize all these rules, here's the big takeaway from our dive into section 3.8 today. We've built an incredibly powerful toolkit.
We really have.
We started by realizing that exponents are just the TLDR shorthand for repeated multiplication. From there, we proved that none of these operations are arbitrary laws.
They're all connected.
The product rule for adding, the quotient rule for subtracting, the mind-bending reality that the zero power traps you into equaling 1, distributing exponents like a delivery driver, multiplying stacked exponents with the power rule, and using negative exponents as elevator tickets to flip fractions.
It's all just logic.
They are all a continuous chain of mechanical logic. If the initial shorthand is true, every single rule we discussed today mathematically has to be true.
It is a meticulously constructed system, and it scales up flawlessly. But, since we started this deep dive looking at the staggering vastness of the universe, that NASA image of our solar system, and the enormous numbers required to simply measure the void of space, I want to leave you with one final puzzle to think about.
Oh, I am ready. Lay it on me.
We established early on that multiplication is just a clever shorthand for addition. Adding the number 5 4 times is just 5 times 4.
Correct.
And today, we spent our entire session learning that exponents are just a clever shorthand for multiplication. Multiplying the number 5 4 times is just 5 to the 4th power.
Yes, the shorthand for the shorthand.
So if there's shorthand for addition and a shorthand for multiplication, is there a mathematical shorthand for stacking exponents on top of exponents?
Wait,
Like, what if you wanted to write 5 to the 5th and then raise that massive number to the 5th power and raise that to the 5th power, building a terrifyingly huge tower of exponents? Is there a symbol for that?
wait, does that actually exist?
It does. It's a mathematical operation called tetration. It represents a level of rapid scaling that makes astronomical distances look microscopically small.
That is terrifying.
It is literally what happens when the exponent shorthand desperately needs its own shorthand. But that is a deep rabbit hole for the insanely curious listener to go explore on their own.
I know what I'm Googling tonight.
For now, the next time you look up at the night sky, or look back at figure 3.44, think about the distance from the Sun to Neptune. Know that you now possess the exact mathematical tools to write that terrifying distance down clearly, cleanly, and without filling up a single whiteboard.